Hello, in this video I'm going to go through question 5 on the Math 2009 paper. So in this question we're looking at tours of n by n grids of squares for n greater than 1, and these tours are such that the path moves horizontally or vertically from the centre of one square to the centre of an adjacent square, and the path starts and finishes in the same square. And also the path visits the centre of each square only once. So for example, this is a tour in a 6x6 grid, which they give us. And we are told for parts 1 to 4, it is assumed that n is even. So for part 1, we need to with the aid of a diagram, show how a tour which starts and finishes in the top left square can be drawn in any n by n grid. So remember, n is even, so if we begin with a n by n grid for n even, then for example here I've done a 6x6 grid, and we know we want our tour to begin in the top left hand corner. And here are our rules for a tour. So we need to essentially fill in this grid going into each square only once. So one way we can do that is just to do a sort of E or cone kind of shape. So if we were to describe in words what we've done here, then what we're doing is travelling right along the top row, then going down a row, then going left to the second column, then repeating this until we get to the bottom row, when we travel all the way left to the leftmost column and going back up to the top. Okay, and in part 2 it asks, is a tour still possible if the start or finish point is changed to the centre of a different square? Okay, so I think instinctively the answer should be yes, because for example, if we started off in the top right corner, then just by rotating the grids, we'll be back in the position that we were in before. So we know there's a tour for this, and then we can just rotate the whole thing back. But how can we see that we can start in any square? Well, here is the diagram we had before, and we see the tour has to go through every square, right? That's one of the things that defines the tour. So was there anything special about starting in this particular square? Well, why couldn't I have just, say, decided to start my tour here and then just carried on following the same path? And it's completely fine. So we can say that because this new square lies somewhere on the original tour, then we can just start in the new square and follow the original tour. So we'll be following back up to the starting point where the original tour ended, but then we can just carry on from the beginning up until we get to our square. And so we can find the tour beginning in any square. Okay, so now we have a robot, and it's programmed to move along a tour of an n by n grid, and the robot understands two commands. The command R, which turns the robot clockwise through a right angle, and the command F, which moves the robot forward to the center of the next square. And the robot has a program, which is a list of commands, which it performs in order to complete the tour. And the command R appears R times in the program, and the command F appears F times. Okay, now for part 3, they tell us that initially the robot is in the top left square pointing to the right. So we're in a situation like this. The robot's in the top left and it's pointing towards the right. And assuming the first command is an F, what is the value of small f? So how many times does it perform the forward move in total? And also they want us to explain why r plus 1 is a multiple of 4. So for how many f commands does it do? Well, the f command tells the robot to move forward to the center of the next square. And so we see each time we do f, it takes us into a new square. Okay, and how many squares do we have to enter? Well, we need to go into each square at least once. Sorry, not at least once, exactly once. And we also need to return to this starting square. And so because there's n squares in total, then that must mean this robot has to move forward n squared times. So we see that f is equal to n squared. Okay, so now we just need to work out why r plus 1 is a multiple of 4. Okay, so let's have a think about what directions the robot is facing. So to begin with, we know that this robot is facing to the right. And after it has gone through all of the squares, then the only way it can get back to this square that it started from is from this one. And so if it's moving from this one back into this top left square, then it must have been going up. And so at the end, the robot is facing up. And r is basically the number of right turns this robot makes. So we know that after the robot has performed the command r times, then that's going to take the robot from facing right to facing up. And so if it performs r plus 1 times, then the robot was facing up, but it's turned right one more time, so it's going to be facing right again. So doing this r command r plus 1 times is going to take the robot back to facing the direction it was originally facing in. Well, if this robot's gone from facing right to facing right again, then whatever it did on its journey, in the middle it must have done some number of full turns so that it's facing in the same direction it was originally facing in. And while there are 4 right turns in a whole turn, so the robot would have turned right some multiple of 4 times, i.e. r plus 1 is a multiple of 4. Okay, so for part 4, we need to figure out if the results from part 3 still hold if the robot starts and finishes at the center of a different square. So for example, if I was starting from this square instead, with these results from 3 that f is n squared and r plus 1 is a multiple of 4, would these results still hold? Okay, so let's think about how we got these results in the first place. So for f, we said that it was because f takes us into a new square, the f command, and the robot enters a new square n squared times. Well, when the robot starts here, the robot still needs to go into each square once, and so the robot still needs to enter a square n squared times. So we're still going to have that f is equal to n squared. Okay, so how about r plus 1? How did we get this result? Well, we said it was because after the robot had performed r times, then it must have turned through 270 degrees. And so if it had performed r plus 1 turns, then it would be facing in the original direction. And so r plus 1 must correspond to doing some whole number of turns. So because there are 4 turns in a whole turn, then r plus 1 is a multiple of 4. Okay, so must this still hold? Will the robot still have to have turned through 270 degrees from the beginning to the end of its journey? Well, the answer is no, because say the robot began facing in this direction and it followed the path that we had before, so this one that looks like an E. Well, then when it gets back to this square, this robot is going to be facing in its original direction. And so we see if the robot had started in this square and taken this tour, then it would have turned through 360 degrees rather than the 270 that it had done before. And actually this would mean that r is a multiple of 4 instead of r plus 1. Okay, so now we just need to show that a tour of an n by n grid is not possible when n is odd. So for example, if I had had a 5 by 5 grid like this, and we can see that what we did before is not going to work, because if I try to do the sort of E shape, then when I get to this square, I'm going to get stuck. I'm not going to be able to loop back around. But for this question, we need to show that a tour is not possible for any shaped paths and not just this particular sort of comb-like one. So okay, let's think about what the robot must do if it were to go on a tour of this grid. Well, it has to start and finish at the same square. So let's just suppose it was this top one. And then because it has to go and get back to here, then anytime this robot moves right, then it must also move left to eventually get back to this side of the grid. And anytime the robot moves down, then it's also going to have to move back up at some point in order to get back up to this row. So if for every right move there is a left move, and for every down move there is an up move, then we can sort of pair these moves up. And so we see there must be an even number of moves that the robot makes in total. So that means F must be even. Okay, but do we know anything else about F? Well, we know that F is n squared, because the robot still has to move into each square once, just like it did before when n was even. But now n is odd, so n squared must be odd also. But we just said F has to be even, right? So this gives us a contradiction, and so we can't have any to us when n is odd.